Good morning, everybody. So, in this lecture, let us discuss on boundary layer theory. We have in the boundary layer theory, first, what is a boundary layer? What is the thickness of the boundary layer? These two aspects in today's lecture we discuss. Number one is what is boundary layer? Second one is how to calculate the thickness of the boundary layer. These are the two aspects which we discuss. Now, today's topic is boundary layer. What is it? That is what the first thing. And the second topic is how to define the thickness of boundary layer and how to calculate the boundary layer thickness. So these are the two topics which we will take in today's class. So if I take when a real fluid flows past a solid boundary, when a real fluid flows past a solid boundary. For example, I take this as some solid boundary, a glass plate like. Now the real fluid flows past this solid boundary. It, when it flows past a solid boundary, now you see this first layer of fluid particles. This red one is the layer of fluid particles. This layer adheres to the boundary. Where is the boundary? This is the boundary. Boundary of a solid. So when a real fluid flows past a solid boundary, this the fluid particles or fluid layer which comes in contact with the boundary has a velocity equal to the velocity of the boundary. That means at the boundary, the fluid does not slip. The fluid rather adheres to the boundary. And this condition is called no slip condition. What is no slip condition? At the boundary, when a real fluid flows past a solid boundary, at the boundary, the fluid layer will not actually slip on the boundary. It adheres to the boundary, and this condition is called no slip condition. Why it adheres to the boundary? That is because of the viscosity of the fluid. Because of the viscosity of the fluid, this layer adheres to the boundary. That means if suppose the fluid is flowing at a velocity, for example, V. Now, such a fluid, when it comes in contact with the boundary, the velocity of the fluid is reduced from V to 0 at the boundary. That means velocity is reducing means that means retardation is taking place. When the retardation is taking place at the boundary, this retarded layer of fluid induces retardation in the adjacent fluid layer. which is flowing just above it. And this retarded layer of fluid again induces basically retardation in this. Like this, the fluid layers which are near to the solid boundary are undergoes retardation. What's that retardation? It does it they won't flow with the same velocity with which they have approached the plate. Their original velocity is v, but when once they touch the plate, when once they approach the solid boundary, their velocity initially at the boundary it is zero, because the plate is, this is stationary plate, this is plate is stationary. So the velocity of the fluid particles at the boundary is zero. So that means from velocity v2, the velocity is brought down to zero here. So this fluid layer induces retardation in the adjacent layer to it. Then that layer is also, its velocity is reduced. Again, this layer, it induces retardation in the next layer. Again, its velocity is reduced. That means there exists a zone near to the boundary where the velocity of the fluid is basically now retarded, and this zone where the velocity of fluid is reduced, this zone is the boundary layer. So that means what will happen? For example, a fluid particle, here you take it, its velocity is equal to zero, but the next layer it may not be zero, it may be a little bit more than zero, but definitely it is much less than the original velocity. If you take the next layer, for example fluid layer, again its velocity is greater than the previous velocity, but definitely it is less than original velocity. Like that, if you take next layer, again here also the velocity is lesser than basically the original velocity, but it takes some distance from the boundary, it takes some distance from the boundary, wherein in this zone, naturally, here the velocity is zero. Here may be a little bit better. 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 But by the time it reaches here, it obtains the velocity is equal to v. So, which is velocity 0 to here. The zone in which the velocity of the fluid changes from 0 at the boundary to the v, that means original velocity. This original velocity is called as free stream velocity. What is free stream velocity? It is the original velocity of the flow. So in whichever zone, this is the vertical distance from the solid boundary where the velocity changes from 0 to free stream velocity, and this zone is called as boundary layer zone. So this you should remember. So let us now write basically for all the sentences in clear. So when a real fluid flows past a solid boundary, a layer of fluid which comes in contact with the boundary adheres to the boundary, adheres to the boundary on account of why it adheres on account of viscosity. That means no slip condition exists at the boundary. No slip condition exists at the boundary. No slip condition exists at the boundary means there is no slip of fluid layer at boundary. Right? That means there is no relative motion between the fluid layer and boundary at the boundary. For example, if the boundary is stationary, if the boundary is stationary, stationary means boundary is fixed, then the fluid velocity at the boundary is zero because the boundary is stationary, right? That means the velocity of fluid layer is brought to zero from velocity v. That means the fluid layer is retarded. It's not acceleration, it is retardation. This retarded layer of fluid induces further retardation in the adjacent layers, thereby, thereby developing a small region in the immediate vicinity, in the immediate vicinity or neighborhood, in the immediate vicinity of the boundary surface, in which the velocity of fluid increases gradually from zero to free stream velocity, free stream velocity v increases gradually from zero to free stream velocity. This region is called boundary layer. Once again, I am writing this is a solid boundary. Now fluid move over this boundary with a velocity v. This is called as free stream velocity. Here the velocity v is equal to 0. Next layer is less, next layer less, next layer less. There exists a zone basically. This vertical distance where the velocity changes from v to v is called as boundary layer region. So this vertical distance where the velocity changes from 0 to free stream velocity, right? Now in the boundary layer region, in the boundary layer region, the velocity changes from 0 to v in a very short distance perpendicular to the boundary. That means here it is, this region is very short actually, very, very short distance. Because of this, the velocity gradient. What is velocity gradient? That is dv by dy. Velocity gradient is high in this region. Therefore, the shear stress is very much appreciable even if viscosity is small, because you know that shear stress depends on two things. One is mu and the other one is velocity gradient. This is viscosity, this is velocity gradient. This is so even if viscosity is less, for example, a fluid like water is flowing, so naturally viscosity is very less. Or a fluid like, for example, you take air is flowing, naturally viscosity is less. But still, actually, this dv by dy is very large, because why? Velocity is changing from 0 to v in a very short distance. What is the gradient if I take it? The change in velocity into the vertical by divided by the vertical distance. That means we are change in velocity is how much? V 0 to v. That means v divided by that vertical distance is very, very, very small. For example, I take velocity is 5 meters per second, for example, right? That distance is, for example, you call it as just 1 mm, right? 1 mm vertical distance. So in a 1 mm vertical distance, the velocity changes from 0 to 5 meters per second. What is the velocity gradient? Change in velocity is 5 minus 0. It is 5 in the numerator. What is y vertical distance? 1 mm. Convert into 10 to 1 into 10 to the power of minus 3. So what is your answer? Shear stress is equal, even velocity gradient, how much? 5 into 10 to the power of 3. 5 into 10 to the power of 5000 actually, the velocity gradient, multiplied by, even if the viscosity is very small, but what is the magnitude of shear stress? It will be very high. So that is why this zone is very important. So adjacent to the boundary, even if the fluid is having low viscosity, the shear stress is very high because of the velocity gradient. From where the velocity gradient has come? Because boundary layer has formed. And boundary layer is a must actually. It is inevitable. Only thing is we neglect, we don't neglect. Otherwise, boundary layer formation on a solid boundary when a fluid flows over the boundary is a must actually. Automatically it forms the boundary layer. Maybe the thickness may be less in certain cases depending on the viscosity. In the flow, velocity is very, very, very high. Thickness may be less, but doesn't mean that the boundary layer is not there. So till now, whatever we call it as, till the what you call it as the pipe flow chapters, whatever we have studied, we never used that word boundary layer. But actually, the Prandtl first time he has introduced this boundary layer, and because of this boundary layer theory explanation, we could get the real solution for many, many of the practical problems. Till that time, we don't know, because we are experiencing it, but we don't know how it has come. Because, for example, for example, an aeroplane is moving. Why there is a resistance to the aeroplane actually when it is moving into the in the air? How much is that resistance? That resistance, as far as we are concerned, if there is no viscosity, is negligible, because we assume air as an ideal fluid, so viscosity is negligible, so naturally resistance, shear stress should be zero. But that is not the case. The resistance is so high. So that is where the answer has come actually. Similarly, when a bike driver is going actually with a very high velocity, why he is getting resistance actually? Why that wind velocity just giving him near his thing more than that? The reason being the formation of the boundary layer. The study of the boundary layer exactly gave the solution why this resistance is happening, and we could able to find a solution for it, for the boundary layer, and how to overcome that resistance to the maximum extent. That answer has come next. Till that time, people never believe why. The reason what we experience, the drag force is experience, the resistance force is experience, but why? That why question is still remaining till the explanation regarding the boundary layer, till the boundary layer is being explained by Prandtl actually. So that is why please remember that. Now what I want to tell to you, i- in the boundary layer region, there exists a velocity gradient normal to the boundary, which is basically very high. So that's why even if the viscosity is very small, still the shear stress is over. So now what I conclude actually here, hence actually we conclude that when a real fluid flows past a solid boundary, the flow is divided into the flow is divided into two regions. The flow is divided into two regions. What is that actually? Number one, flow within the boundary layer, flow within the boundary layer, where the boundary layer effects are considered. So this happens only at the boundary. Then second, flow outside the boundary layer. Outside the boundary layer, basically, where the fluid has ideal fluid flow characteristics. So this is the thing. That means, suppose if I take a solid boundary, this is a solid bound. Now flow takes place over it. L velocity. What happens? I told actually there is a region at the boundary, and this is boundary layer region I mentioned, and this is outside the boundary layer. In the boundary layer region, the velocity changing from v is equal to 0 to, in this vertical distance, v is equal to capital V. But outside the boundary layer region, the velocity is constant. The velocity is uniform. All this place, anywhere you take it, the velocity is uniform. Whereas within the boundary layer region, the velocity changes from 0 to v. That means within the boundary layer, when the velocity is changing from 0 to v, the velocity gradient exists because there is a change in velocity. Outside the boundary layer, when the velocity is uniform, everywhere velocity is constant. So velocity gradient is equal to 0. When velocity gradient is equal to 0, what is tau? Tau is equal to mu into dv by dy. When the velocity gradient is 0, so shear stress is equal to how much outside the boundary layer? 0. But whereas within the boundary layer, tau is equal to mu into dv by dy. And you all well know that mu cannot be 0. There will be some even small value may be there. But because of this, the tau is very high. So that is why we need to discuss. When we discuss flow, basically, we have to discuss in two ways. When flow is taking place for any boundary, solid boundary, right? We have to discuss in such a way that there is a region, immediate neighborhood of the boundary, where the velocity gradient is very high, where there is a change in velocity from 0 to full velocity in a very short region. And beyond that short region, the flow can be treated as here, it is just as ideal fluid flow. So flow outside the boundary layer, you can treat that flow as ideal fluid flow. Whereas flow within the boundary layer, you have to consider that velocity gradient and find the shear stress and see that how much resistance is occurring and how to minimize that resistance that you have to work. So this is what the emphasis of this boundary layer. So now boundary, till now we assumed that there is no boundary layer. That's how we have treated all this Bernoulli's equation, everything we have done based on that. Now what we found actually, there is a region immediate neighborhood of the boundary where there is a change in large change in velocity from 0 to free stream velocity, and that is also occurring in a very short distance. Because of that, the velocity gradient is very high. Because the velocity gradient is very high, the shear stress, which is equal to mu into dv by dy, is very high. Outside the boundary layer, dv by dy is equal to 0. Velocity is uniform, no velocity gradient. So automatically dv by dy is equal to 0. Therefore, shear stress is 0. So that you should be appreciated. Here, tau is equal to mu into dv by dy. So this is the two things that you should remember here. So with this, now what is a boundary layer? Boundary layer is a region. Boundary layer is a region near the solid boundary. Near the solid boundary. Now, when a real fluid flows past a solid boundary, the there is a the first layer of fluid adheres to the boundary. If the boundary is stationary, the velocity of fluid layer is also 0. That means that velocity of the fluid layer is retarded. This retarded layer of fluid induces retardation in the next layer, and that layer induces retardation in the next layer. Like that, boundary layer is a region near the solid boundary when a real fluid flows over it, where the velocity changes from 0 to free stream velocity. This region is called as boundary layer region. Now the next question is, what is the thickness of boundary layer? Actually, there are mathematically, first one is we call it as nominal thickness. Second one is displacement thickness. Third one is momentum thickness. Last one is energy thickness. So let us take one by one. First one is nominal thickness. Nominal thickness means I represent the thickness of the boundary layer as delta. That is general practice. It is the distance from the boundary. It is the distance from the boundary. That's fine. Distance from the boundary, right? In which the velocity of flow reaches to 99% of free stream velocity. Free stream velocity of mainstream. That means if I take this, This is a solid boundary. Now the fluid is flowing like this. So this is the free stream. This free stream velocity is capital V. And we told this is called as nominal thickness delta if the velocity is changing from 0 to 99. So here you know it 0, whereas here the velocity is equal to 99% of this capital V. So that is 0.99 capital V. So then this is called as nominal thickness. So that means when the velocity is equal to 0.99 of free stream velocity. Free stream is nothing but the velocity with which the flow is approaching the solid boundary. The velocity with which the flow is basically approaching the solid boundary. That is what we call it as that. Then second one is displacement thickness. Displacement thickness, momentum thickness, energy thickness equations are very, very important because they show how the velocity variation takes place. What is displacement thickness? It is denoted by delta star, right? That is first thing. It is defined as the distance from the boundary measured. Always this is for all the things you can write. Measured perpendicular to the boundary. For all the things it is same. Perpendicular to the boundary, right? Of this solid body, right? By which the boundary should be displaced. Boundary should be displaced. Boundary should be displaced to compensate for the reduction in flow rate. Reduction in flow rate on account of boundary layer formation. This is the distance perpendicular to the boundary by which the free stream is displaced due to formation of boundary layer. What is it actually? Suppose I am taking this as a solid boundary. A glass plate, you imagine that, right? This is stationary. Stationary solid boundary. Now this is the free stream velocity. Now this is how the boundary layer has formed. So now what has happened here? The velocity is zero. Then the velocity is zero means what happens to flow also? Zero. Then velocity is less, flow also less. So what happens in this region? The flow is basically reduced. That is what precisely he has mentioned. The vertical distance by which this boundary is shifted to compensate to the reduction in flow rate. How much distance you move this boundary? It's only imagination. We don't move the boundary, but we are explaining the principle in such a way. But vertical distance by which the you are moving the boundary to compensate for the reduction in flow. Why reduction has happened? Because the velocity has changed. So how much distance you move, that is what we call it as This is the displacement thickness. And for the displacement thickness, the equation is being given to solve the problem, sir. So what is the equation for the displacement thickness? Displacement thickness is equal to integral 0 to delta 1 minus small v by capital V into dy. What is small v? Small v is nothing but it is not 1 second. Don't say it again, confusion. Small v, I will write like that. Small v, it is a small v, which is equal to the velocity at any point, at any point, but I call it as at any point y from boundary. At any point y from, and what is capital V? It is free stream velocity. So what is finally equation? Delta star is equal to integral 0 to delta 1 minus small v by capital V dy. So what they will do in the exam is they give the equation for velocity. So you need to calculate this. We will do that, no issues. Then coming to third, actually, momentum thickness. Again, it is also distance from the boundary, distance from the boundary of the solid body. Of course, always the distance is measured perpendicular to the solid body by which the boundary should be displaced. Boundary should be displaced to compensate reduction in momentum, because the effects you see, the moment once the velocity is reduced or velocity changes from 0 to v on the boundary, first thing is the flow is reduced. To compensate the flow, the reduction in flow rate, how much we shift the boundary is displacement thickness. Now naturally when the velocity is reduced, its momentum is mv, mass into velocity, that is also reduced. To compensate the reduction in momentum of the flowing fluid, on account of boundary layer formation. So previous one is reduction in flow. Now reduction in momentum. So please note again, this is denoted by theta. Momentum thickness is represented by theta is equal to integral 0 to delta small v by capital V into 1 minus small v by capital V dy. This is second. The last one, what is energy thickness? And this energy thickness is represented by delta double star. Delta star is displacement thickness, theta is momentum thickness, delta double star is this. So this is again it is the distance measured from solid boundary perpendicular to it, by which the boundary should be displaced. Boundary should be displaced To compensate the reduction in energy of flowing fluid on account of the boundary layer formation. So this is the next. And what is the equation for this? Delta star double star is equal to integral 0 to delta. It is small v by capital V into 1 minus small v square by capital V square into dy. So these are the four thicknesses that we have studied. So kindly note that actually the first problem in boundary layer chapter is how to define boundary layer, thickness of the boundary layer, and problem on boundary layer thickness. So this we will take it up in the next class. So in today's class, we have discussed what is a boundary layer, why the boundary layer forms, what happens because of the boundary layer formation, and how to define the thickness of the boundary layer, the various thickness that's we have defined. So here I stop this lecture and let us go into the problems of how to solve and determine the boundary layer thickness in the next class.
Like, share, and subscribe. Hit the bell icon for more updates.